This episode of the HVAC School podcast, as well as HVACRschool.com, are made possible by Carrier. I recently went to Atlanta to meet with some of the ductless and VRF leadership team with Carrier, and I'm really impressed with some of the hires they're making. If you've been in the business for any amount of time, you know that a company goes as its people go. And what I'm seeing with Carrier is that they're hiring some real insiders in the ductless side of things. They're hiring people who actually know the business, who have actually worked with their hands. They recently hired my friend Keith Ledford, who's a guy I've looked up to for years. He was with Trane and then Carrier, and now he's back with Carrier in their ductless division. And hiring people like that makes me really believe in what Carrier's doing in their ductless side. I was checking out some of the new products, especially their performance series of ductless. They have some really nice features. The one that I'm most excited about is the fact that the entire blower assembly comes out with just a couple screws. Because for those of you who have worked on ductless, you know what a pain ductless systems can be to work on. So I'm really interested in what Carrier's doing as far as serviceability of their ductless products and the investment that they're making in that segment. Carrier, turn to the experts. This episode is also made possible by Testo. As I've mentioned before, I'm a big fan of Testo instruments. They have a really good quality for the price point on especially their smart probes tools, their Bluetooth connected tools. I'm a big fan of the Testo 550, the Testo 605i are kind of two of my favorites. I've been enjoying the 770-3 meter. You can find all of these tools by going to TrueTechTools.com. Use the offer code GETSCHOOLED at checkout to get a great discount. Also want to mention the Danfoss app toolbox. You can look up Danfoss on your iPhone, on your Android device, in the app stores, and you can find their free sets of apps. I really like the refrigerant slider app. This is the one I'm using pretty much every day, especially when I'm doing training and I want to reference a pressure-temperature relationship, especially on a new refrigerant. And then actually today's guest is Jamie Kitchen with Danfoss. So those two things are totally unrelated. The apps division and Jamie Kitchen in the training division, they really don't have anything to do with each other, but both show that there's a commitment at Danfoss for technician training and to back the technicians. And I am very proud to work with Danfoss, and I thank them for their support of the podcast.
Help me welcome the man who thinks a sling psychrometer makes him look like a cowboy, so he always shouts "Yee-haw" while using it. Bryan Orr.
I do think that a sling psychrometer is possibly the most visceral and childish action that you can do and still claim to be a professional in HVAC. Really, even in today's, with today's technology, there's no real good reason to use a sling psychrometer if you have a good quality thermal hygrometer or digital psychrometer. But I mean, come on. There's something just fun about pulling that thing out and slinging it around in the air. Anyway, today on the podcast, we actually have a guy who when he came on last time, talked about psychometrics, and that is Jamie Kitchen from Danfoss. Jamie is hailing from Canada, and I will confess that the audio in this episode isn't quite as good as I normally like it to be, but we're doing it over a phone app, and I think it works out. I think you can hear it okay. So we talk about thermostatic expansion valves, TEVs, TXVs, and Jamie talks about some things that frankly are new to me, some new ideas, and I'm sure they'll be new to you as well. Jamie's a smart guy, and I'm glad to have him on, and so hopefully you get something out of this. I did ask Jamie what makes Canadians so special, and the answer frankly shocked me.
To avoid any speculation, I will now allow my precious tiger blood to be extracted. There you go. Those who deserve it now possess it. Use it wisely. I trust that you will.
So how's things?
It's going well, actually. I can't complain.
Good.
Weather's been kind of suckish, but other than that, it ain't bad. I always throw it into a learning opportunity because this is the kind of weather where it's really hard to dehumidify.
So what kind of weather is that in Canada?
Generally, if you look at your charging chart for a piston, you'll notice that on cooler days with a higher latent load, you have tons of superheat. And when you have lots of superheat, what does that do to your average evaporator temperature? It pushes it up, right? So you go further away from your apparatus dew point. Right. And this, of course, kills your dehumidification when that's exactly the time you need dehumidification and not sensible cooling, right?
Got it. Yeah, that's actually interesting. So the first thing to ask there is, like, how many systems are still being shipped with fixed orifices? I mean, it seems like that's pretty much a dying breed, isn't it?
Yeah. SEER 13 came in 2006. So previous to that date, let's just say 5 million units shipped. 4 million of them, or the vast majority, were pistons. Come SEER 13, that pretty much flipped on its head, with the vast majority going out being TXVs, because the TXVs just allowed for not only better or more optimal evaporator fill over various ambient conditions, it also resulted in a tight shutoff when the system shut down. And this maintained your differential across your metering device and across the system. So your compressor had to do less work rebuilding those optimal conditions again on startup. And the more you start, the more impact this has on your efficiency over a period of time, say an hour. So those two things combined gave the SEER 13 effort a big shot in the arm, because just by going to a TX valve alleviated a lot of the issues that were required to get to SEER 13. They weren't all of them, but it was a big jump.
Good stuff to get started with, at least. It was sort of a perfect intro, and that's all because the Canadian weather is, what's the average outdoor temperature up there right now?
Right now it's a high 60s, low 70s, and rainy. It's a little sunny out right now, but there's a substantial amount of humidity in the air.
You don't run the air in those types of conditions, do you?
No. Generally, we have a dehumidifier in the basement, like a standalone dehumidifier that we empty on a regular basis just to keep the basement dry. And we just open the windows in the evening time. Right. So, again, we're cooler than normal. This time of year, we should be in the mid to high 70s with, generally drier weather should start kicking in around this time. But last few years, it's just been up and down. It's either one side or the other.
So let's start with just the term, because I think I've actually had some questions from guys who ask, what's the difference between a TXV or a TX valve or a TEV? And really, they're just names for the same thing, right? What do you call it typically?
I generally call it a TXV. If somebody refers to it to a TEV, I'll just refer back to them as a TEV. Our marketing people will generally sometimes dig in a bit more because they want to stick with a certain protocol, I'll call it. But for the most part, I really don't care. I mean, TEV, if you really want to take the acronym for accuracy, would make more sense. But we've been calling it TXV for so long now that it just seems to slip off the tongue.
So let's address right off the top, because I think a lot of techs are going to be listening to this already with a bad attitude about TXVs. So let's address those feelings, those emotions. First of all, the elephant in the room. What do you think causes the high failure rate that some people see on expansion valves?
That's a good question. I'm going to just go back, I guess, and reference, our warranty pile. You'll hear me speak a lot about the warranty pile, and it's something that as a junior engineer, we kind of get stuck in. And the reason I refer back to that is because it gives you an indication of why stuff is being returned from the field. So again, it follows a lot of what we talk about in compressors. Generally, you can't really flood a TX valve, but what you can do is adjust it way out of whack. And so what we'll find is TXVs that have been adjusted, their superheat has been adjusted either very, very low, and the report comes back that the valve isn't controlling, or it's been put very high, and the report is that the valve is not responding. In other words, the valve is closed, it won't open, and it just is almost counterintuitive to what you would think. The other big issue we find is overheating. Generally, people, I think, when valves are brazed in, my understanding is that you wet wrap this valve so that it's almost, unrecognizable. And then you apply a lot of heat very quickly to the connections because you're in a battle against time. You are heating water up, which is turned to steam. And if you know, like we talk about, you put a pot of water on a burner, no matter how much heat you place on it, it's never going to get any hotter. The steam's going to escape and take that heat with it. And this is what is happening. That wet rag is basically in a race with you to remove the heat as you apply it. So it is actually better to apply more heat quickly to the area you want to braze before it can travel up into the area where the wet wrap is and carry that heat away. Believe it or not, the result of not applying heat fast enough is you're going to run out of moisture against the surface area. You may still have moisture on the outside of the rag, but you're going to dry it out on the inside against the valve. This will stop heat removal and allow the valve to climb in temperature. And we get these valves back where they've been heated so much the diaphragm's distorted, The sensing bulb is actually leaking only because of the great buildup in temperature. So again, practice brazing them in until you get very, very good at it. And the reason I say that is, for example, at a trade school, we donate all kinds of valves that we can't sell for various reasons. And we donate them to schools. And my point is that I'd rather have the students in a trade school braze these things in over and over and over again because they can do it in their sleep. Once that's done, you've eliminated almost half of the reasons why these things fail. Now, when I say that, I'm not talking about systematic failure. I'm not talking about something happening in another part of the system where the valve becomes plugged or something that has absolutely nothing to do with the TX valve itself is occurring. This, of course, makes up for the other third of the failures that come back. And we've got a list of all kinds of things where TX valves are getting plugged. They're full of junk. There's minerals in them. There's leftover debris and everything else. They come back. Unfortunately, once a TX valve gets plugged, unless it has a removable screen, it's done. I hate to say it, no fault founds in there as well. A certain proportion of what we get back is we can't see anything wrong with it. We put it in our test stands. We fire it up. We even take some of them and throw them in one of our refrigeration trainers, and they actually work fine. And we just can't figure out why these valves were actually returned. And again, I think a big part of the superheat misadjustment comes from people not understanding what should happen or what does happen when you adjust superheat on a TX valve.
I wanted to get that out of the way right off the start because I think some people start hearing about TXVs, and especially when we're talking about the positive attributes of a TXV, and a lot of technicians sort of shut down and think, well, it would be better if we just went back to pistons. I definitely fall into the category of a tech who has replaced a lot of expansion valves that were actually failed. The bulk of them were failed because of bulb issues, meaning that when they're actually failed either because, the bulb vibrated and snapped, which happens on certain brands. We run into a lot of those cases. It lost its charge. And then also because of, like you said, issues with overheating and then issues with them becoming contaminated. And a lot of that has to do with proper refrigerant line handling in the first place. So when you do a new install in Florida and you're not careful about not getting the lines in the dirt, and if, let's say, your liquid line filter dryer is inside the condenser, which it is in certain brands, and then you start that thing up, and the first thing that happens is that sand and dirt slams right into that expansion valve. And so that's a reason. And then also the majority of technicians don't flow nitrogen in our market. And I think it would be safe to say that the majority of technicians across the country and the US do not flow nitrogen while brazing. And so depending on the level of oxygen that's in the lines, you'll get varying levels of carbon buildup, also depending on the amount of heat that's used. And so I think that's also why certain people get more failures than others. First of all, you should be flowing nitrogen while you're brazing, but even if you're not, it depends on the way that it's being handled, because you get a lot of technicians who say, I haven't flowed nitrogen my entire career and I've never had an issue. And I think sometimes when you're dealing with situations where they've gone straight from having nitrogen in a system to a fairly closed circuit and maybe one port open and then brazing, that's different than somebody who's, say, brazing in a reversing valve where all the lines are open and they're using really high heat, brazing it in, and then all that carbon ends up in the expansion valve. That's sort of a nuanced look at it. But those are the reasons that I generally see. Rarely do I see that the actual valve itself is just literally something wrong with it. It's almost always something external to it, with vibration being thrown into that same category where it vibrates and then ends up cracking the bulb tube.
Yeah. And the vibration isn't an issue only for TX valves. I mean, pressure controls and temperature controls, even connections on compressors are under that direct attack all the time by vibrations in the system. So yes, absolutely.
All right, so with that out of the way now, let's actually talk about an expansion valve. What is the job of an expansion valve? What does it do?
Well, the job of any expansion valve is to meter the refrigerant into the evaporator to match the heat load on that evaporator. So every pound of refrigerant that boils from a liquid to a vapor absorbs so many BTUs per pound. So if you want to balance the heat load on an evaporator, you take your heat load in BTUs and say BTUs per hour, and you divide that by the amount of heat that's absorbed by each pound of refrigerant, and that's how many pounds you need to put through that evaporator in an hour. So the job of the metering device is to ensure that you get the correct amount of refrigerant flowing through your evaporator to absorb the heat And as well, it needs to ensure the conditions in the evaporator are such that it does the job it's supposed to do, whether it's sensible cooling or a mixture of sensible and latent cooling for air conditioning, whether it's medium or low temp refrigeration. The pressure in the evaporator has to reflect the application. So those are the two jobs that the metering device does. With a fixed orifice, whether it's a cap tube or a piston, it is exactly that. It's an opening. And the amount of flow that goes through that opening is based, all else being the same, the diameter or length of the cap tube, the diameter of the opening of the piston, and the pressure differential across it. So since you can't change the diameter of the opening, only the pressure differential across the orifice will cause the flow to change. So that's why on a hot day with high condensing temperatures compared to your evaporator, you will get much higher flow through it. You'll find a higher evaporator temperature, a higher boiling temperature of the refrigerant, and you'll have much lower superheat. Whereas on a cooler day, say with a lot of moisture in the air, so you have your latent load, and again, all you need to do is look at the charging chart for a piston, you will find that you will have very high superheat because you just don't have enough flow through the evaporator to match your load. This is where the TX valve shines. The TX valve is what we call an adaptive control. And by adaptive, we mean it opens and closes, it adapts to the change in heat load. And it does this with the sensing bulb. So picture your sensing bulb as a little miniature refrigeration container that has an opening with a hose on it that goes back to the element or the power head of the TX valve, the top of it. So it's sitting on top of your suction line. Now imagine you increase the heat load on that evaporator. You suddenly have more moist air coming across it. You suddenly have a heat load, whether it's in refrigeration or air conditioning. Generally, let's say refrigeration. You walk in with a whole bunch of warm product and you put this in your walk-in box. Suddenly, the amount of refrigerant in the evaporator isn't enough to absorb all that new heat. So the liquid runs out sooner, which means it has more time to warm up as a vapor. So the vapor rises in temperature, and when it does so, it runs past that sensing bulb. The sensing bulb picks up that heat, and some of the liquid in the sensing bulb boils, and the vapor takes up more room than the liquid does, so the pressure in the sensing bulb rises. Now, because you have that cap tube running to the power element on your TX valve, that pressure is transferred to the top of the TX valve. So the TX valve is kind of like a balance beam, so to speak, on its side, where you have underneath pushing up the evaporator pressure and spring pressure. And I'll get back to that in a little bit. And on top, you have this pressure from the sensing bulb. So picture a line with the sensing bulb pressure on top and the evaporator and spring pressure underneath. Well, when that bulb pressure increases like that, it pushes down on the diaphragm, and the force it's pushing down with now becomes greater than what's underneath it, the evaporator and the spring pressure. This forces the valve open, and the valve now opens more, putting more refrigerant into the evaporator to match the new heat load. This results in somewhat of a drop in superheat and more refrigerant flowing into the evaporator now to take care of that extra heat. And of course, vice versa occurs. TX valves aren't as susceptible to pressure differences like a piston is. They just require enough pressure in order to be able to feed properly. So I'm not sure if you understand how, say, a gas valve works, a gas regulator. It'll always give you 3.5 inches of water column pressure out as long as you have a minimum amount of pressure going in. It just regulates the pressure. Right? It can't create pressure, it just regulates it. And that's very similar with a TX valve. The TX valve will cause a pressure drop, and it will offer enough refrigerant as long as there is a great enough pressure difference across it. So that is in a wrap-up how a TX valve works. It senses the temperature of the refrigerant leaving. If it climbs compared to the saturation temperature in the evaporator, it signals it needs more refrigerant. It then opens up and puts more refrigerant in. This is where an understanding of superheat and subcooling come in. You have to understand that a TX valve doesn't maintain constant superheat, right? It requires an increase in superheat in order to open the valve. So if you look at the opening curve or the opening profile of a TX valve, under high load, you will have higher superheat than what you will have under low load. So if you're in pull down mode or you have a high latent heat, you're going to have higher superheat. If you're almost satisfied or the air is very dry in the house, say for example, you're going to have less superheat. You won't see the climb in superheat like you would with a piston, but let's look at that spring. Because you need to compress that spring underneath in order to open the valve, that spring is going to push back harder as you load it. So it's going to require a greater force on top to hold that valve open against that increased spring pressure. And the only way to do that is for the sensing bulb to be warmer. So the sensing bulb is going to have to be a few degrees warmer than the saturation temperature to keep that valve fully open or open more than it would, say, compared to when the valve was almost closed. So instead of seeing an 18-degree rise in superheat or 12-degree rise in superheat with a piston, you may see a 3 or 4-degree rise in superheat with a TX valve, but it will not maintain constant superheat in the evaporator. All right, and I think some people are confused about that. So let me ask you a question, just out of curiosity.
Go ahead.
If I were to mention factory or static superheat, what would you tell me that means?
Factory or static superheat.
They use them interchangeably.
Okay. I would think that means design superheat. The constant superheat is designed to maintain. I'm going to
Yes.
feed right into your desire for my question.
That's a very popular answer, and unfortunately it's wrong. Static superheat is the superheat required to overcome the spring force. The spring is never completely uncompressed in a TX valve. Okay? It's always going to push. And it's designed to push down with a certain amount of equivalent force. So this brings us to nominal capacity and things like that. So a 45-degree evaporating temperature, air conditioning situation. If your valve has 7 degrees written on the side of it, okay, that means that it will not even start to open up until you have 7 degrees of superheat. That is the static superheat. So the valve is fully closed until you have at least 7 degrees. And when you modify your superheat, you take that dial and you turn it clockwise to increase it or counterclockwise to decrease it. What you're affecting is the static superheat setting on the valve. So once again, it is not what the valve is designed to maintain. It will never maintain a constant superheat. The superheat's going to change based on your load. So the valve won't even open until you actually hit your static superheat. Static means not moving. And so that's where that comes into. Now, engineers like to make lots of things out of nothing. Okay, I don't mean that literally, but we have multiple superheats. The second super we talk about is opening. So if I were to go talk to an OEM engineer and they would ask me, what is the opening superheat on this valve? They're talking about how many degrees of superheat is required above static to give me the rated capacity of that valve. So between being fully closed and being fully open, let's say the rated capacity is 1 ton. I may need 5 or 6 degrees of opening superheat on top of static before my valve gives me my capacity. Now, if you add those two together, that gives you operating superheat. And operating superheat is what everybody refers to when they measure superheat at the evaporator outlet. So if somebody calls me and says, I have 12 degrees of superheat at my evaporator outlet, they're referring to operating superheat. And if the system's under load, it'll be 5 or 6 or 4 degrees at least above the static or factory superheat setting on a TX valve. That's where that value comes from.
Very interesting. I've literally never heard that before, ever.
No.
So this is me learning here as I listen. Makes sense, though, because that's often what you'll see. You generally, when you measure the actual superheat on a system with a factory valve, you're generally going to see superheats that are higher than what the valve will often say. Mm-hmm. And I guess that kind of makes sense.
Yes.
Interesting.
It's alleviated a little bit by the rise in evaporator pressure in the evaporator as you dump more refrigerant in. But again, it's always going to result in a little bit more superheat under high load than what you would get, say, when you're almost satisfied. So I just thought that's an interesting thing. So remember, it's not uncommon for a system to have high levels of superheat. And when I say high levels of superheat, I'm not talking 40 degrees. I'm talking 12, 14, whatever it happens to be, out of your evaporator when it's under high load. The last thing we want somebody to try and do generally is adjust superheat when you're under load, because if the system is doing what it's supposed to do, you're going to be hitting a moving target. In other words, your superheat should be dropping as the load is satisfied in the space. So the key thing here, okay, or maybe foreshadowing a bit, is if it's doing its job. If you're not making pull down and you have really high superheat, that's a different story. Now you need to go out and find if your high superheat is related or not, right? But you need to take other things into account. This idea that a TXV maintains constant superheat, I think, has caused quite a bit of confusion in the market. And, I can't blame people because, hey, we talked about pistons. Prior to 2006, there's a lot of people that never ran into TX valves or very rarely ran into them unless they were in refrigeration. And even then, if they did commercial refrigeration, half the time it was a cap tube. So when TXVs came on the market, there was a huge effort in education and training for people because, again, there was just not this knowledge available. I think another part of the issue that makes people upset is this TX valve is like this little black box, and a lot of OEM TX valves aren't adjustable for superheat. In other words, there's nothing to fiddle with. There's nothing you can physically change on it to make it work. So if there is something that's not working, it's pretty easy to see this TX valve and think, oh man, this must not be doing what it's supposed to do because the conditions in my evaporator aren't what I want them to be. The system's not pulling down, whatever. I'm going to change this TX valve out because there's nothing else I can do with it. And this is where the whole systematic troubleshooting, as you mentioned earlier, very rarely is the TX valve itself that is the source of the problem. Rather, it's just the collector of dirt or, the thing that's feeding the evaporator that's closest to where we're picturing a problem. So I get that part 100%. So maybe we can spend some time just going through, yes, we'll talk about TX valves and best practices, but let's look at some of the other things that may be causing problems that isn't the TX valve.
All right, so in today's Tooltip Corner, I want to bring up a couple things that come up a lot when you're talking about digital gauge manifolds. And so first off, I've said this a bunch of times, but I just want to restate it because a lot of technicians ask, why would you want to go digital? And, all it does is just do math for you. Well, it's not quite that simple. An analog set of gauges does not have the level of accuracy that a digital set has. And so accuracy and being able to have all of these measurements right in front of you in one place is one of the big reasons that you go to digital, not because it does the superheat and subcool calculations for you, because that's not a big deal. And so for those of you who like looking at the needle, I like looking at the needle too, but there's reasons why you may want to consider not doing that anymore when it comes to accuracy. One of those reasons is that most of the thermometers that we use to measure lime temps are K-type thermocouples. That it's little, it looks like the little tiny pitchfork, with the two prongs that we use. And there's a lot of manufacturers that use that. And it works okay, but it does not have the accuracy of a thermistor type measurement. And so the Testo, both their smart probes and the 550s, 557s, they use a thermistor instead of a thermocouple, which means that both the pressure measurement's going to be better than what you get on analog, and because you're using a thermistor instead of a thermocouple, you're going to have less variance, which means that instead of potentially having a situation where you think you have 10 degrees of subcool and you actually have 5, you're going to be much closer to that 10 degrees of subcool if that's what your target is. So there's an advantage there. But there's another couple things to think about. There are some manufacturers of manifolds who integrate the micron gauge into the manifold. And Jim Bergman talked about this in the last podcast. That's really a bad idea because you want your micron gauge to be reading as close to the equipment as possible, and you want to be able to valve it off in a very solid way, in an actually valved off way, in order to measure your decay. And the only way to do that is with an actual vacuum rated core tool, because your handle on your vacuum pump isn't sufficient for valving the system off. And so if you are doing it even on the handles of your gauges, those a lot of times the seals will leak under a very deep vacuum. So you need to be able to do it on a vacuum-rated core tool. Well, if the micron gauge is built into your manifold, first of all, you're pulling through a manifold, and you're probably using 1/4-inch hoses. The manifold's a restriction, and it's closer to the pump. Now your micron gauge is closer to the pump than it is to the system, and you want it to be closer to the system. When you do your decay test, you want it to be as close to the system as possible. Well, the Testo 557, it has a micron gauge, but the micron gauge is external. So it's a separate micron gauge that then attaches back to the actual head unit, the actual manifold, which is the right way to do it. So you have the data there on the manifold that you're used to using. It's right there with everything else, but it's a separate sensor that attaches to the system, so you can do a proper decay test, which I think is a really nice thing. And that's probably my favorite thing about the 557 is that option. And it also has the additional, port for the vacuum. So if you're gonna pull a vacuum through your manifold, I think the 557 is probably the best option. And again, this is my opinion. I'm not saying there's anything wrong with the other brands per se, but for this reason, I think this makes it superior. Now, again, we don't even suggest you pulling a vacuum through your gauges, and so you can still use the 557 without pulling through it if you want. You can still use the micron gauge on it. You just aren't going to have your hoses connected to the system anymore. So I know that's a little bit confusing. So the thermistor is something to look for. Having a vacuum gauge that's not built into the manifold itself, but it's external to the manifold, is something to look for. And then finally, the other thing that I suggest is look at temperature compensation. There are some, even the Testo Smart Probes, for example, they're not temperature compensated, and so with very, very fine pressure measurements, it's going to be affected by the temperature. So for example, you wouldn't want to put, and I don't know a case where you would do this, but you wouldn't want to take a pressure reading in a highly variable temperature environment when you're taking regular pressures. But when you're measuring vacuum, that's where it becomes really important, because you're reading very, very fine changes, and if it's not temperature compensated, then you're going to read all over the place. And so the 557, the 550s, they have temperature compensation built in, which makes a big difference, especially even when you're dealing with things like the standing pressure test to see whether or not you're dropping pressure over time with a nitrogen test. Temperature compensation is also important with those types of readings. So there's a lot of reasons to look at temperature compensation. All of this to say, when you're buying a manifold where you're looking at something to take superheat and subcool and take system readings, look at temperature compensation, look at whether or not it's using a thermistor or a thermocouple, and think about the location of your micron gauge if you're going to be measuring vacuum with your manifold set. All right, that's enough for me. Let's get back to Jamie. I guess I need to address this because I've said on this podcast before, I've called a TXV a constant superheat valve, and frankly, I never considered the idea that you do have increased spring compression and the fact that there's always going to be a lag in response to. So your superheat actually has to increase for that valve to open, which makes perfect sense.
Yes.
But it is important to at least recognize that the superheat is an indication of evaporator load.
Yes.
And so while it's completely true that it is not a constant superheat valve in the sense that it always maintains exactly the same superheat, the intent of the design is to maintain the proper amount of refrigerant flowing through the evaporator coil to match the load. And superheat is a measurement that we take that indicates that. So the two are very closely related to each other, just not constant in the sense of what you're saying, that say you have a refrigeration box and you fill it full of product. You can't expect that expansion valve to run exactly the same superheat that it ran when it had no product in it. Or you can't expect a system that's running on a high humidity day to run the exact same superheat that it runs on a very low load day, for example.
Mm-hmm.
So I wanted to address that. And then let's go over quickly the forces. So you talked about this, the spring pressures, closing pressure, the evaporator pressure, which is often on the outlet of the evaporator on the external equalizer. So it can be either internally or externally equalized, but most modern expansion valves that we see are externally equalized. Well, in air conditioning especially.
And that's an important point, actually. Do we have a second to touch on that?
Yeah, go ahead and do that, yeah.
Okay. The external equalization connection is there for a reason. And generally, I'm not big on rules of thumb, but if you have a distributor, in other words, a refrigerant distributor, in other words, you have a multi-circuited evaporator, your default should be an external equalized valve. Here's the thing. If you install an external equalized valve and you don't really need one, you're fine. Install an internal equalized valve and you need an external equalized one, now you're going to have problems. Because generally, the TX valve, if it's internal equalized, can only sense pressure, right, at its outlet. In other words, that outlet pressure is allowed to travel up under the diaphragm. If you have a distributor downstream of that, that causes a pressure drop, and all distributors cause pressure drops, sometimes as high as 20 pounds per PSI or more. The result is the expansion valve, I hate to use the word think because it doesn't think at all, but it thinks that the pressure in the evaporator is 5, 10, 15, 20 pounds higher than it really is. And that higher pressure is up under the diaphragm. Now, when you combine that with the spring pressure underneath the diaphragm, what is applying pressure on the other side of that diaphragm? Your sensing
Just the bulb,
correct?
Right.
Now, your sensing bulb is measuring superheat, which is the rise of temperature above saturation. Saturation is determined by pressure. So if the pressure inside your evaporator, let's say, is 10 or 15 pounds less than what the TX valve thinks it is, that means your saturation temperature is also correspondingly lower. Let's say 6 or 7 degrees lower than what the TX valve thinks it is. So if you need 7 degrees of superheat to open up the TX valve, but the evaporator is 6 degrees less than what it thinks it actually is, you're going to need 7 plus 6 degrees, or whatever the saturation temperature drop is across the distributor, in order to open the valve. So the greater the pressure difference between the outlet of the TX valve and where the sensing bulb is, and you use an internal equalized valve, the more or the equivalent superheat is going to be required to open the valve. So if you have a 5 degree drop across the distributor, you're going to require 5 degrees of higher superheat to open up the TX valve. So you're going to constantly underfeed the evaporator if you use an internal equalized valve in a high pressure drop multi-circuited evaporator.
That's interesting. I never made the connection. I always knew it was because of pressure drop across the evaporator coil, but I never made the connection in my brain that, a distributor is what's going to be creating that additional pressure drop on one coil over another coil.
Yep.
It's very interesting. It's almost like you have a second metering device in place in addition to the expansion valve.
Well, in a sense, that's what you actually have, yes.
Right.
You literally have 2 metering devices in a row, really, in series. And that's an interesting point. But that's where the external equalization connection comes in, because it takes the pressure after all these pressure drops, where the sensing bulb actually is located, and applies that pressure up under the diaphragm. The evaporator or the TXV outlet to the evaporator, okay, that pressure is not allowed up under the diaphragm in an external equalized valve. It's sealed off. Only the pressure coming in from your external equalization line can be applied under there. That's why you never, ever, ever seal off that external equalization line, even if you don't need it, because the valve will not work. It always has to have access to the system.
Right. That's something that we've probably all seen at one point in time, is a technician that says, well, the old one didn't have this tube, so I'm just going to seal it off. Well, no, if your new one has the tube, it's using that as the actual pressure point to access evaporator pressure to put it up under the diaphragm. And so that's actually the opening force. Now, one thing that's interesting, because I had been saying for years that if you have a plugged or crimped external equalizer, because the external equalizer is the opening force, is the closing force. I think I said opening force earlier, because it's the closing force of the valve, that if you have it crimped, that the valve will go wide open. What I found out in practice is that the valves will actually often leak some static refrigerant into those equalizers, and in fact, it will actually cause the valve to slam shut. Mm-hmm. I didn't realize that. I mean, I had some kind of expert refrigeration guys say that, you can see both, but you actually will see cases where a external equalizer being blocked or crimped shut will actually result in lower suction pressure, lower evaporator pressure. And my thought was always that it would be higher. Have you seen that at all?
Well, yeah. See, if it's plugged, then generally you can't force anything out of it. So when you try and push the diaphragm down, especially if it's got liquid in it, you can't compress a liquid. So you can't close that valve down, right? So it's actually literally going to stay in the one position it's going to be in. And that's a good point. I'm trying to visualize it in my head so that if it's trapped with a high pressure underneath it, you can't relieve it. If it's trapped with a low pressure underneath it, you can't relieve it. So I guess it all depends on the throw of the die, right? But I would definitely know the valve would be very laggy. It would be very, very, very slow to react in that case, almost like a pressure control where the capillary tube, or capillary tube, as you guys call them, is full of oil. You're trying to push this oil through a small diameter tube. It's going to move a lot slower than the gas pressure would, resulting in a much slower reacting control. That's a great thought.
Yeah, and I'd always just said, well, if it's crimped, then you don't have that closing force. And if you don't have the closing force, then it's going to go wide open, right? That made sense to me. But as it turns out, it really just depends on the particular situation and the particular valve too. So
Yeah,
anyway,
no, that's a good point.
Interesting stuff. So, but it still is good to know that if you have an externally equalized valve, that external equalizer acts as a closing force, the spring acts as a closing force, and the bulb acts as an opening force, which is why when you do the old practice of taking the bulb and warming it up in your hand, you'll see the valve open because more pressure is being exerted inside that bulb as you add additional heat to it, which then acts as an opening force to drive the valve open.
And that's a great tech tip we can throw in here, right? That it's doing two things. You're one, checking your bulb charge to see if it's still good, right? But two, it's kind of one of those last ditch things you can do that instead of dialing your superheat all the way in, till the screw practically falls out, just hold that bulb in your hand. And if the valve's got a plug in it, not so much in the filter screen, but say it's got some crud in the actual stem somewhere that's causing a lot of hysteresis or whatever, hysteresis, right? You can apply enough pressure differential across it by the heat of your hand to often overcome that gumminess and unstick the valve. Now, obviously, the problem hasn't gone away. You've just put a patch on it. You still got to figure out why the valve's sticking, which means you probably have to clean the system. But my main point here is you've identified where to look. Okay, and that's key to any troubleshooting is eliminate as many possibilities as possible so you know where to focus on. So, anyways, I thought I'd just throw that in there.
Sure. It's a good thing to do. The one thing that I see techs do sometimes is they do something that they've been taught to do, like warm up the bulb, but they don't know what it means when they're done. So they warm up the bulb and they say, oh, okay, so my suction pressure went up. Okay, now what? It doesn't have any significance or meaning. So let's go through some common diagnostic steps of diagnosing an expansion valve. So first off, I guess let's address the issue of why most technicians start looking at the expansion valve. And I think it's generally, for the bulk of technicians out there, it's just as simple as I've got low suction pressure. I've got low suction pressure. I've got some subcool. Because I've got some subcool, I'm pretty sure it's not charged. So now I'm going to start blaming the expansion valve. So speak to that a little bit.
Okay, well, you hit the nail on the head. First of all, I congratulate them for actually checking the subcooling at the condenser outlet, because the subcooling of the condenser outlet is generally your indicator that it's not a refrigerant charge. So looking at your evaporator, if your evaporator pressure is low and it's multi-circuited, look for changes in between circuits. Let's say you've got 5 or 6 or 8 circuits. You can have multiple circuits that are plugged, either with oil or kinks in the line or whatever it happens to be. And this can literally drop your pressure substantially in the suction line because the header collects all these different circuits together. So it's not so much a TX valve problem as a distribution problem. Okay, and the easiest way to do that is, especially if you got one of those infrared thermometers everybody sees, you shine that on your coil and it will give you a beautiful temperature profile of the coil. Okay, and if you see certain circuits that start off at very low temperatures but end up at much higher temperatures because they don't have much refrigerant in them, then that's an indicator that you're starving certain circuits. And this is going to be an issue that needs to be corrected. Okay, it has nothing to do with the TX valve generally, but it still needs to be corrected. So little things like that. If you happen to have a TX valve that has a removable filter in it, you can check that. But even before you get to the TX valve, look upstream. Okay, yes, you've got subcooling at your condenser, but let's change this into an electrical situation. If you happen to have 24 volts at your control transformer, but you have 0 volts at your control relay, what do you generally do? What's your next step?
Right, you got to move down the line, see where you're losing it.
Absolutely. I could show you pictures of filter dryers where the last half or 3/4 inch of that filter dryer is white. And it's not frosted paint that we put on there, it's ice, right? Because the filter dryer is plugged. Solenoid valve's not functioning properly upstream. There's a valve in there, valve somewhere in there that somebody forgot to open properly. There's all kinds of things that you need to check upstream. And to be honest with you, it's very quick. Just go along with your hand. And if you happen to feel a temperature drop, or if you happen to hear something with your ears or see it, right, there's a good indication that there's a pressure differential across there. Again, if you want to get more precise, you can use a thermocouple with a little bit of insulation. Just walk along and feel across each component. Remember, there's a lot of times when you only have 4 or 5 degrees of subcooling. And this can occur when it's low ambient. It can occur when you have low load, things like that. It doesn't take much pressure drop to eat up 4 or 5 degrees. So once you get flash gas feeding the metering device, especially if it's excessive, you can't push much vapor through a TX valve. This is going to drop your evaporator pressure substantially. Okay. If the evaporator pressure is not very low, let's say it's supposed to be 45 degrees and it's 28 degrees. You got to picture what a TX valve does. If you have reduced airflow on your evaporator coil, let's say you got a plugged air filter, what's that TX valve going to do in response to the reduced load on the evaporator?
It's going to slam on down. It's trying to feed it with the proper amount of refrigerant, and it's saying we got too much.
Yeah, exactly. It's going to throttle closed. Now, you got a fixed speed compressor. What's the only way for that compressor to balance the amount of refrigerant the TX valve's putting in there? If the TX valve reduces the refrigerant flow, what's the only way that compressor can balance that reduced flow? The only way to do that is for your evaporator pressure to drop. The lower the evaporator pressure, the lower the pumping capacity of the compressor. So it is natural for the evaporator pressure to drop when the TX valve closes, because that's the only way a fixed speed compressor can balance that reduced flow. And that's exactly what the system is trying to do all the time. It's trying to find its balance point. My question would be, how much superheat do you have? If you've got a 30 or 28 degree evaporator temp and you've got 8 degrees of superheat, it ain't a TXV problem. It's an airflow or load problem. Now, if you've got a 28 degree evaporator and you've got 30 degrees of superheat, now it's a refrigerant flow problem. Okay, it's not a load side problem. So those two different results right there require a different approach to the problem. Airflow is not going to be fixed by putting a new TX valve in there. That has to be addressed. In other words, you need to find out, why am I not having any heat load? Is my evaporator iced up like a complete block? In other words, maybe my airflow was a little bit low to start with. I started building ice. I started building more ice, which acts as an insulation. This reduces heat flow, on and on and on and on. It perpetuates itself. Or do I have, say, a blocked filter or a blocked screen on my TX valve, and I'm just not getting any flow through it? In which case you would end up with a low evaporator temperature and very, very, very high superheat. Now, in this case, you would see ice on the inlet of the circuit because you do have a little bit of refrigerant going in there, okay? And it's below freezing, so you're going to have ice on the beginning of the circuit. But the rest of the circuit is going to be very, very warm, okay? So this is a good indication that you don't have enough refrigerant going into the evaporator. That's all that tells you. You confirm your refrigerant charge with your subcooling. That is not a refrigerant charge problem. You check upstream to eliminate any possible blockages that could be causing flow issues. Then once you remove that possibility, now you focus on the TX valve. Okay? So you can try adjusting superheat. Generally, if you try adjusting superheat, as soon as you try reducing superheat, you should see an immediate response if the valve is reacting. So if the valve is reacting, it's got a proper bulb charge, and it's just a superheat problem. In other words, somebody was monkeying around with your superheat before you got there, then you should see an immediate response when you try and reduce superheat. The valve will immediately open up, your evaporator pressure will increase, you'll have more refrigerant flowing through the system. So now what you need to do is you need to adjust it. In the case of AC, for example, some of the AC valves, you can back them all the way in and then so many turns back out and you hit factory setting again. Otherwise, if you don't see any change when you adjust to superheat, then that means either the valve is plugged, stuck, or you've lost your bulb charge, one or the other. So unfortunately, at this point, you can try holding that bulb in your hand to see if the valve pops. In other words, pops open. If not, here's what I recommend you do. When you pull that valve out, rather than just replacing it, and this is very important, rather than just replacing it, if it's got a removable orifice, pull that orifice out and look at the screen. If it's plugged, you have to ask yourself, why is it plugged? Where's my filter dryer? Why didn't the filter dryer pick up on this? It's an important question because if you just stick that TX valve back in there again, you got to ask yourself, if that filter dryer didn't capture this debris, what's to say that there's not more of this stuff floating around that can possibly plug this? Generally, I would recommend flushing the system. You don't want to have your TX valve act like your filter dryer. It is not there to clean the system up. That's not its job. Okay? If you've got a split system and your filter dryer is, 30 feet away on your liquid line, try moving it closer so that it offers, better protection. Maybe there was a lot of work done on that liquid line upstream of the TX valve. As you say, people didn't use nitrogen. It doesn't take much of that copper oxide to block that screen on the TX valve. So maybe move the filter dryer closer. But my point is, you've identified why that TX valve failed. If it's a removable orifice, great. Just clean the screen, put it back in again. But even if it's a fixed orifice, if you look into the liquid line inlet of the TX valve, you will see the screen. If that screen is plugged with black stuff, then you know it was contaminated. It's important because you have to understand why the TX valve failed before you can replace it, just like a compressor or anything else. How can you guarantee it's not going to fail again until you have cleaned up or remedied the reason why it failed in the first place? Okay. And just my own curiosity as a tech, I always wanted to know. I just hated replacing something and not knowing why it failed because I was never guaranteed it wasn't going to happen again. And it just bugged me, but that was just me. So to me, that's a big deal. So also, if some of that stuff makes it past that screen and into the distributor lines, what's to say that it isn't going to cause problems there as well? So just flush the system, clean it up, replace the valve during your commissioning, make sure that it runs properly, pulls down okay, things like that, and away you go. But again, don't automatically assume and just replace the TX valve without at least taking the steps we mentioned before.
Absolutely. Yeah. And so here's what I would say, because I think as we kind of travel through these conversations, sometimes it's easy to get kind of lost in it. So start here. We're going to just, again, refer to the issue of, seems like my high side subcool liquid temperature / condensing pressure is about what I would expect, but my suction's low. This is where techs start with, okay, maybe it's the TXV. And so before you start thinking the TXV, let's really identify, is it a load issue? Meaning we don't have enough heat load on the evaporator coil. That would be low airflow. That would be, it's primarily low airflow, but it could also be the actual low load in the space. You could have somebody who set their thermostat to 62 degrees and let it get down there. And then that'll, of course, be low load as well. Florida especially, because we always set our units at the hairy edge of freezing in order to remove as much latent load as possible.
And it makes sense.
But anything that causes low load, that can cause low suction pressure. Or is it refrigerant flow? If it's refrigerant flow, then you're going to be running a high superheat at the outlet of the evaporator. If it's low load, then you're going to be running a low to normal superheat at the outlet of the evaporator. So do that first. Once you've identified whether it's refrigerant flow and you believe that it is refrigerant flow, now do like we said. Just because you have a 10-degree subcool outside doesn't mean you don't have a pressure drop and therefore a temperature drop across the liquid line. So take your temperature outside, compare it to the temperature of the liquid line going right into the evaporator coil, right before it hits the TXV. See what it is there. If you have a significant temperature drop, that could very well be your problem because the expansion valve can only do its job if it has a full line of liquid.
Correct.
If you're looking at the air handler and you hear the liquid line going, well, that right there tells you that you're not feeding a full line of liquid to your expansion valve, and so it can't do what it's designed to do at that point.
Exactly. And
if you've identified that you do believe that it's a flow issue, you can pull out your handy-dandy thermal imaging camera. That would be a great tool to use. Take a look at the evaporator coil, take a look at your components, and look for pressure and therefore temperature drops or changes. And if you don't have that, then you can do the old-fashioned test that we used to always do when I first started in the trade, which is unhook the blower and let the coil start freezing and look for irregular freeze patterns. That will also be an indication of where restrictions may.
A great idea. I've never heard that one.
Oh, really? Yeah, we used to do that all the time. That was common practice.
Yeah. Oh, okay.
Yeah.
Yeah, half the time the air's so dry, but I just want to kind of throw this in there because you're talking about all the pistons that were out there. Keep in mind that a large part of what we talk about with the drop in pressure of the evaporator and temperature due to reduced load, this is a TXV specific thing because a piston will not throttle closed at all like a TX valve will. it will continue to put that refrigerant into the evaporator, possibly flooding your compressor. So again, that's the benefit of a TX valve. But you will see a drop in pressure in your evaporator because you won't be evaporating the refrigerant as much. But I don't believe, at least in my experience, it won't be as excessive as what you would see with a TX valve, which will just starve the coil. It won't starve the coil. It will just throttle back and reduce the feeding because you just don't have the refrigerant there to evaporate it. And this causes a much more rapid drop in pressure. So if you're not used to a TX valve and you're used to a piston and you see this, wow, my evaporator temperature is way below what it's supposed to be, right? Well, again, it could be an air side and the TXV is doing exactly what it's supposed to do. So, you don't want to blame the TX valve in that case.
Right, exactly. And that's exactly what happens. And Florida is rather unique in this regard because we have such high relative humidities. And so what happens is you go up to a unit and you find that it's freezing. And I actually had a guy in one of the groups was talking about a system. He's running low suction and low superheat. And so he's going to put an expansion valve in it to fix the problem. And I'm like, dude, don't do that. When you put an expansion valve in it, the thing is going to drop the evaporator temperature even lower because it's going to throttle to keep the superheat higher than what you currently have. When you have a lower evaporator temperature, you're going to freeze even sooner, because you're running a lower differential. So it's more likely that you're going to freeze, and especially when I talk about in our market, because units freeze so readily down here because we're always on the hairy edge of freezing anyway, based on how we set them up and then add in our really bad ductwork.
Do you just reduce the airflow? Are you running like 320 CFM per ton or something?
350 is sort of the base, but we run enhanced mode. We run a lot of dehumidification control. And so if you run a system, Carrier used to have the old super dehumidify where you drop the DH and you drop G. And so you'll be running, under 300 CFM per ton in some cases. And so if you do the math on that, if you're used to a design temperature drop of, 40 degrees or 35 degrees on your evaporator, you're going to be below ambient. You're going to be running even at 75 degrees inside. You're going to be running at freezing or below freezing in some cases. And so we're constantly on that sort of hairy edge trying to get as much latent removal as we can. And so TXV just doing its job with any sort of decreased load conditions is going to result in a freezing evaporator coil, because all it takes is getting that evaporator coil below 32 degrees Fahrenheit and you start building up ice eventually, given enough time.
Well, I see an opportunity for sales here, man. So you can sell defrost kits now, man. Time termination.
Evaporator defrost, huh? Okay. Yeah, that's just what we need to do now is re-evaporate all of that moisture right back into the airstream.
Oh, yeah, I know.
We'll have mold crazy in all the ducts and I'll blame Jamie Kitchen.
Anyways, that's interesting because, again, I talked to a guy from the Comfort Institute or something like that. Anyways, they do air balancing and air testing and all this kind of stuff across the country. And they have this huge database. And I asked him, Al, I said, what's the average airflow in residential systems that you guys have? Because I know you keep these databases. And I think he said something like 289 CFM per ton. And I said, what? I said, isn't it supposed to be 400? He's like, yeah, I wish. He said 289 CFM a ton. Now, again, there's thousands and thousands of points that they tested on these things, right? Different applications. But just think about this. If you see a low evaporating temperature and you automatically assume it's the TX valve, what are you told to do to the superheat to increase the flow to the evaporator that you think is causing the low evaporator temperature? The first thing they tell you to do is reduce the superheat. Right. So you're reducing superheat, you're increasing refrigerant flow on a system that doesn't have enough airflow for the load it's got now, right? So you're actually doing the exact opposite of what you want to do or should be doing unless you verify your airflow. And as we all know, airflow is one of those big challenges that seems to go unaddressed many times, but I guess we're kind of getting beyond what we want to do here. So
it's related in that I think expansion valves get blamed on functioning systems because the expansion valve's doing its job and the issue is evaporator load. And the issue with evaporator load most commonly is low airflow. So I think what happens is a tech will go out and say, oh, the expansion valve's bad. And so then he'll get a new expansion valve, he'll put it in and realize, oops, the expansion valve's not bad. Well, we're still going to go ahead and do a warranty return. Well, that's embarrassing. And then they'll find some other reason. They'll work on the airflow or whatever the case may be, maybe tap up the blower or something.
Mm-hmm. Well, airflow is not easy to fix if it's ductwork. I mean, you go to somebody and say, hey, man, your ductwork's got to be all thrown in the trash and redone again. That's not a couple $100. That's one that I would imagine most people would not want to go to a homeowner or customer and say, this is what you need, right? Let's try and find a workaround solution to having to do that,
So we saw a lot more of that back when PSC motors were the standard, when PSC motors were the bulk of what were going out in new equipment. That was very common. So you'd have a system, it would be in for 9 months, and then it would start freezing up. And so now technicians have this mindset of let's prevent freezing at all costs. So they do all this crazy mumbo jumbo and blame TXVs and do all this. Now with X13 motors and variable speed motors being the standard, especially of what we're installing, those things will maintain their airflow all the way up to 0.8, to 1.4 inches of static in some cases.
Wow, that's amazing. Really?
Very close to their design airflow. So with that being the case, that now the complaints are, well, the thing's noisy. It sounds like it's going to come apart. But then the other issue is that a lot of the issues we see with airflow are just the way that they're set up, where they're being wired into the improper terminal. They're wiring it to the Y1 terminal instead of the Y/Y2 terminal. So the thing's never ramping up to its full airspeed. A lot of times it's just proper setup that's being missed, or the X13 motor's not being tapped properly based on the static pressure. So the technicians don't know how to measure the static pressure and then tap the X13 motor. And that's largely what we're seeing now. The ductwork's still bad, and it's resulting in higher power bills now and air noise and failure of the motors, but it's not resulting in the old problem of the unit freezing as much because of the amount of static that it will overcome.
Interesting.
Which is probably a good thing for the expansion valve market, because you'll probably see fewer of those as those motors become more ubiquitous. And obviously it depends. Furnaces are still more prone to it because furnaces don't come with case coils on them. They don't come rated with the filter. And so they are still rated at 0.5 static, whereas a fan coil, which is largely what we work on in Florida, we have 90% fan coils. They come rated already with the coil in place, with the filter in place at 0.5. So you've got 0.5 inches of static to work with. You can have pretty bad ductwork if you have 0.5 static to work with and still be okay.
Interesting.
But anyway, I think the thing I want to kind of wrap up here with is just that you have to follow good, clean line practices when you're installing TXVs. Make sure you're not getting dirt in your lines, obvious stuff. Place filter dryers in the proper locations. If you are field installing a filter dryer, I always suggest that you put it in the liquid line by the evaporator coil, the closest to the expansion valve, to help protect that valve.
Absolutely.
Obviously, follow proper evacuation procedures. If you're getting sludge in your system because you have moisture in the system, that's going to result in a lot of expansion valve failures. Flow nitrogen when you're brazing to prevent you from getting flakes in there. Make sure to keep from overheating the valve. Wrap it well. Most guys nowadays don't wrap anything. If it's a new piece of equipment, for example, they're just brazing in, and all the while that expansion valve may only be 2 inches away from where they're making that braze joint, which of course will result in issues. If you have a system that is prone to vibration-related cracking of the lines, then do something in order to help with that. A lot of cases, it's just a matter of a little foam tape here and a zip tie there, and you've got that resolved. So keep an eye out on that, even when you're doing maintenance or when you're commissioning a new piece of equipment. And then finally, when you're actually setting up an expansion valve, one thing that was a big eureka moment for me on this, Jamie, is it not being a constant superheat valve, which is a very good point that you make there. Don't expect a TXV to maintain an exact dead-on number throughout all load conditions, because it's not going to do it, although it will stay much closer than you're going to see with other types of metering devices. But then see, is it a refrigerant flow problem or is it a load problem? If it's a load problem, fix the load problem. That's got nothing to do with the expansion valve. If it is a refrigerant flow problem, then go through every other possibility before you condemn that valve.
Yes.
Did I hit all the high points here? What did I miss?
Yeah. The superheat is your friend here, even though you charge the subcooling with the TX valve, and 100% back that up, right? And I could spend 10 minutes talking about that. But superheat is your friend when helping you determine flow issues on a TX valve. Once you have eliminated system charge as a possible issue, and you've gone and eliminated all other possible liquid obstructions, your superheat will tell you if it's a refrigerant flow problem or if it's an airflow problem. If it's an airflow problem, low superheat. If it's a refrigerant flow problem, as in not enough refrigerant for the load, then it's going to be high superheat. Okay, so remember those two things, and it'll serve you well in doing this. And again, you hit the nail on the head when it comes to brazing the valves in. These are actually a pretty fine-tuned piece of equipment. That diaphragm is a piece of high carbon, high tensile steel, and it is heat treated. And if you allow it to warm up with a torch too warm, it will take the temper out of it, which basically you're throwing the life expectancy in the toilet when you do that. It's also not going to track superheat with a darn. So it's going to be hunting. It's going to be offset all the time. So again, take the time, wrap it, use lots of torch, keep it pointed away from the valve. Again, read the manufacturer's installation instructions. And especially when it comes, if I can just jump again, to superheat adjustment. Remember, people, each valve model has a different rate adjustment. We have air conditioning valves that are 1 degree of superheat change per full turn. We have some that are 4 degrees of superheat change per full turn. So you're either going to dial it down or out of whack so fast you're not going to know what happened, or you're going to be sitting around all day waiting for something to happen. Okay? So again, this information is not you got to travel 500 miles and attend a course to learn. It's right on the side of the box, or it's on the product data sheet, and with our smartphones, we can get this stuff. You're saving yourself time. Okay, so just spend a few minutes and prepare, and it'll pay you back big time in reduced service calls.
Very good. I think we could talk about this a lot longer, but I think we'll wrap it up here. I do want to talk about electronic expansion valves again at some point in the future, because we didn't really touch on that, because that's a really interesting emerging technology. And another thing we didn't talk about. Another thing we didn't talk about is the required pressure drop that an expansion valve needs and how that's affected by low ambient conditions. And so that's another thing I'd like to talk about sometime. So
I love these talks, these conversations, because I learn stuff too. So
I do every time. I haven't done an interview yet that I haven't picked up something, but what you said about the constant superheat is going to stick with me. That's something I'm going to think a lot more about and do more research on, because that's a fairly new concept to me, but it makes perfect sense.
It doesn't maintain a constant temperature in the evaporator either. Remember, the TX valve is darn what the temperature your evaporator is.
Yes, I've heard a lot of guys say that. I mean, I just heard that just the other day as well. That's what the TXV does, is it maintains a constant temperature of the evaporator. It's like, oh boy. We can talk about automatic expansion valves if you want.
There you go. I was just going to say automatic expansion valves. Remember those things?
Yep, I do. We had a frozen sign in trade school that had an automatic expansion valve on it.
Maintain a constant pressure does the exact opposite of what a TX valve does, right?
Yep.
It closes on a rise and load and opens on a fall and load to try and maintain constant loading, a constant pressure and temperature in your evaporator.
And a frozen sign's a perfect application for that. So that's one case that makes sense, I guess.
So it's frozen yogurt, but that's a different thing.
Yeah, maybe. All right. Well, I appreciate it, Jamie. Thank you so much.
No worries. Pleasure. Take care. Thank you.
All right. Thank you for listening to the podcast. I think this was a good one. I like this one. I really like Jamie. I hope he comes on the podcast more. I'm very thankful to all the people who have been coming on the podcast lately. And this was never intended to be an interview podcast. It's a training podcast. And so I'm going to do some more just sort of basics on the podcast. But there's just so many great people who are willing to come on, and it makes it too tempting, So anyway, we're going to be looking to produce more episodes than even we are right now. We've been doing about 2 a week, but we're looking to even ramp that up some more. We got more videos coming out all the time. We got the tech tips, and I think you're gonna enjoy some of the stuff that's coming up. If you're not subscribed to the podcast, I would suggest pulling out your phone. If you have an Android, go to the Stitcher app, download Stitcher, and then look up HVAC and subscribe to the HVAC School podcast. If you have an iPhone, then go to the Podcasts app. So if you go down to the search feature on your phone and just start typing in pod, you'll find the podcast app. Subscribe to it there. If you're listening to this on YouTube or on Facebook or something like that, that's not the best way to consume this. It's not, the quality's not going to be as good, and it gets interrupted easy. It's just not quite as nice. So using an actual dedicated podcast app is a great way to listen to a podcast. Thank you for being here, and we will see you again very soon on the HVAC School podcast. Oh, one more quick thing. My friend Zach Ciota from Working Joe's Roundtable and the Cowboys of HVAC podcasts, he sent me a song. He didn't title it, but I'm going to call it Ode to R22. Enjoy.
I wish I had my 608 for something I would do. I would not have that blue can no more, that new 22. I wish I had that sweet green can, I'd use it all the days. I'd take that blue thing from my truck, yeah, I'd throw it all away.